Greetings everyone. In a preceding video, we looked at a voltage-controlled filter. Based on a state variable filter, the critical frequency or resonant frequency is controlled by an external voltage. Really useful device. And this raises the question, is it possible to configure this filter such that we can get control over the width of the resonance? In other words, its Q. The answer is yes. I'm Professor Fiore, and I'm going to show you exactly how to do that. Yes, and it's time for the return of the son of the state variable filter, and that would be a voltage-controlled filter with Q control. Pretty cool, eh? All right. Quick reminder of where we came from here. There's a series of videos that you should have watched before getting into this one. Could be confusing otherwise. There's one on the state variable filter, one on the operational transconductance amplifier, and of course the directly preceding video, which is on the VCF, the original VCF. So just to get your mind into gear, right? Little overview on the VCF. Essentially, we're talking about a filter that you could use an external voltage, DC voltage, some kind of programmable voltage, can be AC, that will directly affect what the critical frequency or the resonant frequency of the filter happens to be. So I change that external voltage, and that critical frequency changes along with it. We would typically use state variable filters with this, which is what we did in the preceding video. But this concept, the overall concept, can be applied to all different kinds of filters. Now, why bother? Well, first of all, it's the speed. You can change the critical frequency very quickly with this, much, much faster than you could ever hope to do with a mechanical potentiometer. It can also be programmatic. In other words, you could either create a circuit like a low-frequency triangle wave or sine wave oscillator to control the frequency. You could use some kind of programmatic thing through a, let's say, a microcontroller, that would produce an output signal through a digital analog converter. That's really nice. So it's a much more flexible kind of circuit in that regard. You don't have to literally get your fingers onto a knob to change it. The downside, of course, is it's a more complex circuit and it's a more costly circuit. And this concept can be extended, right? At the last video, I had mentioned that you can, in fact, change the Q or the gain of the circuit with voltage control. Now, change of the gain is no biggie because that is just a VCA, a voltage-controlled amplifier, and we've also talked about that in the OTA video. But, this is an interesting question. Can I get a separate control voltage? In other words, now have two control voltages, one to control the critical frequency and another one to change the Q. That might be pretty interesting, right? Okay, so let's take a look at where this whole thing started, and that was with the state variable filter. Now, I'm not going to go through a really protracted explanation of this, but I do want to just sort of jog your memory a bit here. Right? So this is a 4 op-amp configuration for a state variable filter. We start off with a summing amplifier followed by 2 integrators. The integrators have frequency response that falls at 6 dB per octave, or 20 dB per decade, as frequency increases. So if you were to do a Bode plot, right, here's your amplitude, here's your frequency, you basically see something that goes like this, right? It's just this little diagonal line falling as frequency goes up, all right? That's what they do. And then what we do is we feed some of the low-pass signal back to the summing amplifier, some of the band-pass signal back to the summing amplifier, and we have these 3 outputs, high-pass, band-pass, and low-pass. Okay, now a real quick explanation of how this works. First, let's make an assumption that this output is the high-pass output. And ultimately, this little thing we're going to go through will prove this is the high-pass output, but let's just start with that. In other words, this thing allows the high frequencies through, high pass or low cut if you prefer. So you could think of this as having a response, again a Bode plot that rises up to a point, the resonant frequency, the critical frequency, and then flattens out, right? So it starts at low frequency, comes up, and then flattens out, right? That's our high pass response. And this would be, the slope would be 12 dB per octave because this is second order. There's two integrators in here. Now we run that into an integrator. So the integrator has this falling 6 dB per octave response, and the high pass, the initial part of it is rising at 12, right? So when you combine those two, now it's only rising at 6, right? It's coming up at 12, but then you're going to cut this thing at 6, so you're left with a rise of 6. And the flat part, the part that was the pass band, right, that was 0, right, 0 gain or 0 dB per octave, it's not changing, that is now cut by the integrator, so that falls to 6. In other words, the bandpass output would be rising 6, hits resonant, and then falls at 6 dB per octave. Clearly bandpass. Now you take the bandpass, you run that through another integrator, and that sort of tilts the whole thing all over again. So the rising 6 meets the integrator's falling 6, that leaves you flat at 0 dB per octave. And then the falling 6 plus this falling 6 gives you a falling 12. In other words, a second order low pass response. Now you take that low pass response and it will be inverted because these two inversions cancel, and we do have the original inversion through here. And I add that to the original. Of course, adding an inversion is subtracting. So think of your full bandwidth signal, and you're going to subtract off the low frequencies. What are you going to be left with? If you get rid of all the low frequencies, what you have left is the high frequencies, right? A high pass output. Beauty. Now, you take a little piece of the bandpass, in other words, just the signals around the critical frequencies, and you sum those back in with a variable gain, and now you can affect the response right around the critical frequency, and that controls the Q, right? The width of that resonant peak, okay? So this little op amp down here is our little Q control, and Q is essentially programmed by two resistors, R6 and R7. This ratio gives you the Q. So right now I've got 100K and a 10K, so that's going to give us a Q of 10, a fairly high Q. All right. Now, the way this is configured, you get a pass band gain, in other words, for the high pass and low pass, the flat parts, of 0 dB, unity. But the resonant part gets the gain of Q. So this thing has a gain of 10, a voltage gain of 10, which translates into a decibel gain of 20 dB. In other words, right at the resonant frequency, in this case, just about 1.6 kilohertz, this is going to have an increase in gain of about 20 dB. Now, that might be too much. So what we can do is we can monkey with R4, this input resistor, to change the base gain. All right, and I just have a little note here, increase R4 to decrease the gain, because this is really just, a summing amplifier. You make R4 bigger, what ends up happening? Gain goes down, right? Because the input gain is essentially R8 over R4. So I make this bigger, we get less gain. That pushes down the passband gains. And if you want to get that resonant peak to be right at 0, then you just set R4 equal to R6. All right? So let's just do a real quick analysis on here. I'll do a little real quick Bode plot. So I'm going to run from 100 up to 10K. Let's see what we get. And get the legend down here. All right, so the dark green here is the low pass, which is what we would expect. Comes up, hits the resonant point, falls off. The red, maroonish, whatever you want to call it, that's high pass. So this is coming up, right, rising. This is the cut area, hits the resonance, then goes into the high pass region over here where it's, again, flat at 0 dB. And then, we have this sort of olive green right in the middle, which is the band pass. All right, notice the peak. Right, this was supposed to be at 1.59 kilohertz, and that's just what it looks like. We can verify that if we really want to with a cursor. Bring this up right around the peak, and we're sitting at 1.586. Okay, just within the accuracy of this graph. All right. So that looks good, and you notice that the gain is 20 dB, as we said. All right. So far, so good. Now, the next thing we did was to turn this into a voltage-controlled version. How did we do that? Well, we focused in on R1 and R2. What's the function of R1 and R2 with the integrator? Basically, it's to take the voltage coming out of the preceding stage and turn it into a current. Remember, the inverting input on this op amp in this configuration is at virtual ground. So virtually all of the voltage coming out of this op amp drops across R1. That creates an input current. And because the current into the op amp itself is small enough to ignore, all of that current flows through C1, and that becomes the charging-discharging current of C1. So if I have a small resistor in here, I'll get more current, which means this thing can charge faster, right? Charge and discharge faster. And that is what winds up affecting your critical frequency, 1 over 2 pi RC, all right? And then the same thing, of course, happens over here. And we would make this integrator the same values as this integrator because we want everything to be nice and symmetrical. All right, so we focused in on here and we say, okay, I need something that I can control that will take the input voltage and turn it into an output current. I mean, resistor works really well here, but we don't have an easy way to control the resistance, short of using a potentiometer, but there's the mechanical issues with that. Now, it is possible to use a light source and a light-dependent resistor. That can work, but a nicer sort of way, programmatic way of doing this is through the use of an OTA, an operational transconductance amplifier, because after all, that's what we're looking for. Voltage to current, input voltage, output current. So that ratio of the output current to the input voltage is called transconductance. Remember your FET theory, right? Field effect transistor theory. So an OTA is designed to do just that. It's to take an input voltage and turn it into an output current. So we essentially replaced these resistors with OTAs, and we wound up with this, right? So here's the integrators, and then here's the OTAs, right? So this OTA plus 2 resistors, voltage divider, replaces that 1 resistor. Remember, we need the divider out front because OTAs cannot handle large input signals. You put more than a few hundred millivolts in here, and you're going to get tons of distortion out. So we have to divide the input signal down with the divider so that we get a nice quality signal coming out of here. But the cool thing about the OTA is we can hook up, right, this pin, this control pin, pin number 1 here, on this particular one, the 13700, which is a fairly popular OTA. Originally came out, I believe, in the mid-late 1970s. It's been around for a while. But in any case, that current they call the IABC, very inventive name, and we can generate that through in our simulation anyway, with a power supply and a resistor, our ABC. In your application, this could be something like a low-frequency oscillator, or this would be the output voltage from a microcontroller's DAC, so that you could like I said, write a program, some kind of output signal that you want this thing to create, to emulate. In other words, like you sort of rotating the knob, but in a very accurate and repeatable sort of way. All right. So what winds up happening here, certainly an increase in complexity, but now we can control what that critical frequency is. All right. Well, I'm not going to go through that whole thing. There's a video on that. But the observation, right, pops up. Can I use this same idea, replacing the resistor with an OTA? Can I use that same idea on the Q part of it? In other words, going back to the state variable filter, the original state variable filter, can I use that over here? In other words, can I stick an OTA where R6 is? And the answer is, yeah, you could, and that will work. Now you put the OTA in here with the other resistors and so forth. You hook up a new control voltage for the Q, and bingo, you adjust the input current coming into here, which ultimately will affect the signal coming out, and it would be like changing R6, all right? So, yeah, you can do that, but it turns out there's a nicer way, and that is really to just deep six this whole thing. In other words, get rid of this op amp and R5. Because what's the operation of R5? Why is it there? It takes the output voltage of this op amp and turns it into an input current for the summing amplifier. Hey, wait a minute. Isn't that what we saw over here? Isn't that the job of this resistor and this resistor? Yeah. So why don't I just take the OTA, deep six this op amp right here, just put the OTA here, and then I can connect its output directly into the summing node. Yeah, let's check that one out. So here we go, right? Have to have the little attenuation, the little voltage divider up front, but here's the output coming right out into here. And I've attached this other power supply, right, this little DC power supply, so we can monkey with this in the simulation. And that goes through a little resistor, again, creates the set current, the IABC current, which controls the transconductance, which controls the amount of current coming into the summing amplifier, which affects the signal around the bandpass, and therefore affects the Q. All right, beauty. So I have a little note over here. Higher VQ, in other words, higher control voltage for Q, yields lower Q. So I've initially set this to a Q of minus 10. Let's do some analyses. All right, so I'm going to do the same kind of plot I did before. Little Bodie plot here. Let's see what we got. Hey, look at that. Does this look vaguely familiar? All right. On the preceding one we did, right, we had this. Now, these are not necessarily going to line up perfectly because I just threw in this VQ of minus 10. But, you know, we've got this gain, the passband gain sitting around 0. We see the peak right at the resonant frequency, again, 1.59 kilohertz, and then falling off, okay? 3 different kinds, band pass, high pass, low pass. So for this circuit, right, we see something very similar. So since this thing is not peaking up at 20 dB, it looks like this thing has a slightly lower Q than the preceding circuit, right? Because again, the gain of the preceding circuit, right, also was the same value that we had for Q, right? So 20 dB is a gain of 10. The Q on that circuit was also a gain of 10. So as an equivalent, right? And besides, if you just go back real quick here, right? This looks a little bit more narrow than this does, right? I mean, the scales are slightly changed, but this looks a little bit fatter. And in fact, this is a slightly wider, in other words, a slightly lower Q. But we can go in and start monkeying with this, right? You know, well, you want to try something a little bit tighter, right? So let's go down to like minus 12. And we'll redo this. All right, that's clearly a bit tighter, right? Notice the gain has popped up over 20. We're sitting up 24 maybe, somewhere around there, okay? Still same general shape though, all right? Passband gain still 0. You got the 3 versions, right? The band pass, high pass, and low pass. Everything looks really good, right? A little bit fatter. So let's go the other way. Right? So if a higher VQ yields a lower Q, we started at minus 10, I'm at minus 12, let's try 0. Remember, we can go up to and down to nearly the power supply. Now, a comfortable range on this would be like plus and minus 12. If you really start pushing the envelope, you can start seeing more distortion. All right, so I'm going to stick it kind of like in the middle here, right, of the total possible current. So, and by current, I mean the IABC. Wonk. All right, clearly much broader, right? Much more broad. It's the broaderest so far, right? But there's the center frequency, and again, the passband gain's about 0, right? So that pops up, off you go. Well, you know, in some of these instances, like, you know, back here, there is a pretty high resonant peak. That might create distortion. You put your signal in here. I mean, this thing has a gain of probably somewhere around 20, 30, you know, whatever it works out to. I mean, 20 dB is a gain of 10. So if you had, you know, 26 dB, and, you know, what did I say? It looks like maybe 24. 26 dB would be twice that, you know, a gain of, ordinary gain of 20. So, you know, we're getting pretty far up there. You know, if your input signal was half a volt, 3/4 of a volt, and it was around the resonant frequency, that might start clipping, right? So you might decide, if you're going to use a high Q circuit here, you might decide to move the base gain down. In other words, this this area right in here, the pass bands of the high pass and low pass. And the way you can do that is to just change the value of R4. Right? So I can maybe bring this up to 20K, 50K, something like that. And that would push this end down. The whole set of curves would get pushed down, and you could get this peak down to a nicer area. Maybe +5, maybe 0. You might want it to be the maximum, right? You might want to have the peak be right at unity gain, 0 dB. So that's one way of doing that, all right? But you can monkey around. And of course, if you really push this, you can get basically no resonance. If we bring this up to like maybe 10 volts, the peak there won't be much of a peak at all. Right? I mean, we're only getting like maybe 1.5 dB, 2 dB a ripple on this thing. And that's a 10. I've got a little bit more to go, but we basically have pretty much high pass, low pass, and very simple bandpass filter. All right? But it's all controlled by, that resonant peak is all controlled by this voltage. So, like I said, this could be something like a low frequency oscillator, maybe a triangle wave or a sine wave that's like a few hertz. And now you can have that resonance sort of pulsing, right? If this was, 5 hertz, then you're going to see that resonance come in and out at that rate, 5 times a second, right? So I think that's kind of cool, right? So you can do that. And then the obvious question is, can I combine them both? Can I have 2 control voltages and have one for the frequency, right, and one for the resonance? And the answer is, yeah, sure, why not? And you wind up with this. Okay, so this is up here. This is basically the original circuit that we had for the VCF, and then this little mod down here for the Q control. So here's the control voltage for the Q, and then here's the original one we had as far as changing the frequencies. Okay. Practically speaking, the original state variable had 4 op amps, right? You had these 3 up top, the 2 integrators, the summer, and then we had an op amp down here for the Q, which you could create with a single quad op amp like a TL 084 or 074, sort of a workhorse BiFET op amp. You could go to a higher quality op amp like maybe an LF like 412, which is a dual 411, which is the next generation, also BiFET, but much lower offset and drift characteristics, which would be nice. Similar bandwidth and slew rate. So, that would be a nice upgrade. Here, the numbers in terms of the op amps don't quite work out. The 13700, if I remember correctly, is available as a dual. So in the original circuit, you'd have 1 quad op amp and then 1 dual for the 13700. Now we have 3 op amps and 3 OTAs. So, you can still use a quad, right, for the op amps. You'd have an extra op amp, which you could maybe use as an input buffer, because right now the input signal only sees 10K for a Z in. So maybe a high Z buffer over here would be good. Maybe an output driver might be nice on whichever one of these you're going to sort of focus on. High pass, band pass, low pass. That's a possibility. I think I would kind of lean towards having an input buffer with that extra op amp. Then you'd have an extra OTA. So, what are you going to do with that? Well, one possibility would be to stick the OTA out here and use the control on that to create a VCA, a voltage-controlled amplifier. So now you could have 3 controls, one for the frequency, one for the Q, and then one for the amplitude. All right. The 13700 does have an output buffer on it. It does come with a little Darlington transistor. So I've left those open. We don't need them in this application. But the OTA video explains how to use that. So you could use that. You wouldn't need an output buffer, right? That would be pretty nice. You'd have used all of the components completely, and you'd have a pretty nice, very sort of flexible, controllable sort of combination VCF with Q and VCA. There's multiple ways of doing it. This is probably the easiest way to do it. And, until next time, this is Professor Fiore saying, take care. Have a good one.